Good afternoon, all of you. Welcome to the Water Resources Engineering 2, the fourth unit on the diversion works. We have already seen in the last class about what is a diversion work and what are the various types of the diversion works and what are the various components and what is the layout of this entire diversion head work. And the functions of each of the component we have seen in the previous class. Today's class, we concentrate on the causes and failures of the weirs and barrages on permeable foundation. When a weir is constructed, when a barrage is constructed, for both the cases, the foundation is permeable. As a result of which there will be flow of water, surface flow may be there, or the flow through the foundation also is possible. This sometimes may cause the failure of the structure. So what are those causes? How the failure occurs for these weirs or barrages? And what are the remedies for these failures? Also, we see one more topic like silt ejector and silt excluder. So this figure we have seen in the previous class also, looking at the various components of a diversion headwork. We have seen this is the main weir wall. This main weir wall may have a under sluice portion also, either on both sides or one side. So this is called under sluice, also called the covering sluice, and added to that side you may have a canal also like this. So this under sluice or covering sluice may be there on both the sides of the banks of the weir, or even one side also, depending on how the water is required to be diverted. So you have a major weir wall and then under sluice, and we have a fish ladder and divide wall will be there, and these are all the guide banks and marginal bunds are provided here. Guide banks and marginal bunds are provided here. So if this is the direction of flow of water, because the weir is constructed here, there will be a rise of water level temporarily, which may allow the water to flow into the canal, maybe a left bank canal or a right canal. So the water is allowed to flow into the canal. To the maximum extent possible, we try to see that when the water is allowed into the canal, it should be free from the sediment and the silt. So certain measures are to be taken in this is a diversion structure itself to see that almost clear water, anyway full clear water anyway is not possible, almost clear water should enter into the canal, So what extra devices are to be provided, we will see here. Apart from that, we also concentrate on the failures of these weirs or the barrages. So in the last class, you have seen the distinction between a weir and a barrage also. However, both the structures perform the same function to raise the water level temporarily so as to enable the water to flow into the canals. So when a weir wall is this, and this is the weir wall, maybe on the upstream side, also on the downstream side, there will be sufficient foundation which is provided for resting this weir. On the upstream side, this side portion. So these are a flow direction. So this side also on this downstream side, certain foundation is to be provided. So on this foundation, this weir will be resting. So we try to see what are the causes of failures of this weir because of the flow of water and what are the remedies that are required to be taken. Apart from that, we try to see silt controlling measures also. When the water is entering into the canal, we try to see that almost a clear water should enter into the canal, and what are the devices that are used also, we will see. Causes of failures of weirs on permeable foundations and what are the remedies for these weirs. If you see here, So when the flow of water is taking place here, what type of problems may be there? The water may come through to the downstream portion, and which flows through this bed which is provided here. So this is the downstream bed. Similarly, on the upstream of this weir also, other side also, there will be a concrete bed or a masonry bed which is provided. So what type of failures would take place when the water is flowing, maybe over the surface or beneath the surface also. So the diversion networks are usually provided in the reaches of a river where permeable foundation exists, maybe on the upstream side or on the downstream side. Whenever a weir is constructed, we provide the good foundation also. This good foundation is meant for resisting various forces which are coming onto the weir and to see that the weir is safe. Weirs constructed across the river on these foundations are subjected to surface flow as well as seepage flow. Flow of water over the surface flow. Seepage flow beneath or through the body of the weir. Beneath or through the body of the weir, the seepage flow. So the seepage flow may cause the failure of the weirs either by piping or rupture of floor due to uplift or rupture of floor due to suction caused by the standing wave, also called the hydraulic jump, which may be formed on the downstream portion. Then scouring on the upstream and downstream sides of the weir. So there are 4 possible causes of failure of the weir on a permeable foundation. One is that piping. Second is rupture of a floor due to uplift pressures which may be acting. Similarly, rupture of floor due to hydraulic jump formation and scouring on the upstream side and downstream side of the weir. These are the possible causes of the failure of the weir. So if we just look at the cross section of a weir, in the earlier case we have seen the plan where we have a weir wall. So this is the weir wall which is resting on this foundation. This is the foundation. This foundation is extending on the upstream side as well as on the downstream side. Apart from that, you may have certain block protection works also on the upstream side as well as an apron on the downstream side. So for this weir wall, if a crushed shutter is provided, the water level can be stored up to this portion. So what are the possible problems when the water is getting stored on the upstream side of a weir, whether you have a gate, whether you have a shutter or you don't have a shutter? For both the cases, the purpose of the weir is to store the water temporarily here. If there is no shutter that is provided up to the top of this weir wall, the water will be stored. Thereby, the crust level will be equal to the pond level, or the crust level will be equal to the top of this weir wall. If a gate is provided, the pond level or crust level can be increased up to the top of the crest shutter. So this is how the water will be stored here. What are the possible failures? When the water is stored here, there is a possibility that the water may seep through the foundation of this weir. It may seep through the foundation of the weir. So this seeping water may lead to the failure of this structure. The failure of this structure. So the water which is seeping through this foundation may exit at the downstream portion, or it may cause uplift pressure for this portion, for this downstream portion of the weir. So when uplift is created, naturally the foundation may burst. So bursting of foundation may be leading to the failure of the weir. Also, when water is flowing over the body of the dam or over the crest shutter here, so there will be possibility of hydraulic jump formation at the downstream portion. Why this hydraulic jump is formed? Because you have a change of state of flow, because your water is falling from a high level to a lower level, leading to conversion of energy into kinetic energy. So this is leading to the change of state from supercritical state to subcritical state at a certain portion, at certain length towards the downstream side. Because there is a change of state from subcritical to supercritical, supercritical to subcritical, there is a possibility of hydraulic jump formation. So whenever hydraulic jump is formed, because there is huge mass of water which is flowing with huge kinetic energy, there will be impact on the downstream portion of the weir, on the downstream portion of the weir. So this portion may be subjected to huge impact because of the falling water and thus forming the hydraulic jump. So because of that reason, there may be scouring that may take place. So the downstream portion may fail because of this impact of the hydraulic jump which is acting. This is another cause of failure of a weir. One more thing is that there may be a problem on the upstream side and the downstream side. The scouring may take place. Rupture of flow due to hydraulic jump, there is scouring on the upstream side and downstream side of the weir. So these are all the possible causes of failure of the weirs. So if you understand this cross section, probably you can proceed fast for the remaining things. So just to explain to you that we have taken a typical weir where we have both upstream side as well downstream side of this weir wall are sloping. It could be vertical also, and you have a crust shutter provided leading to the storage of water up to this level known as the crust level or pond level. Since the water is stored here, this stored water will have a tendency to flow through the foundation of this weir, leading to the failure. It may be a piping failure, as indicated. It may be a piping failure, or it may be a rupture of the floor due to the uplift caused by this flowing water beneath the foundation of the weir. Third one is that because the water is falling from the upstream to the downstream portion, hydraulic jump may be formed, causing to the rupture of the floor on the downstream portion. And there may be scouring on the upstream side or on the downstream side because of the velocity of flow of water. So these are all the four possible causes or types of failures of the weirs on the permeable foundation. Let us try to look at quickly one by one. Say piping. It is also called undermining. What is this piping? As the water percolating to the foundation emerge at the downstream end of the impervious floor, the hydraulic gradient referred as the exit gradient may exceed certain critical value of the soil. As a result, the surface soil starts boiling and is washed away by the seeping water. So with the removal of this surface soil, further concentration of seepage flow takes place, and this results in removal of more soil. So coming back to the previous figure, what is this piping? So when you have a change of hydraulic gradient, which is also referred to as the exit gradient, if this value is exceeding the critical value, then there will be a problem of boiling. Surface soil which is available here at the downstream portion may boil. That means it comes out, it gets detached from the floor. Since the soil is getting detached from the floor there, naturally with the flow of water, it will be washed away by this water. Because there is a flow of water, first of all, there is a seepage, because at this downstream portion, the boiling condition may take place for the soil, and the soil particles may be washed off from its original position. So with the removal of this surface soil, further concentration of the seepage flow takes place, and this results in the removal of more soil. So once a small part of the soil particle is removed, quite naturally, it gets exaggerated, it gets enlarged in a shorter span of time. You can see here, if you have a weir wall like this, at the downstream portion, there may be a boiling condition leading to washing away of the soil particle. Once the soil particle at this portion is getting washed away, then the soil which is available here also tries to move up. Once this soil is moving up, because of the flow of water, this soil also gets washed off. So continuously, the erosion of the soil takes place beneath the body of the weir, and finally it joins to the upstream portion, and something like a pipe type of thing will be formed. So this is how the failure is called piping or undermining. Look at this figure. You have certain depressed floor, mass concrete floor provided for this weir wall. This is a weir wall or a barrage, and you have a mass concrete structure which is provided. Then what is happening? The boiling condition may take place here, and slowly the water which is available in the upstream side tries to flow along this arrow and finally join here, maybe leading to a pipe type of thing which is being provided beneath the foundation, leading to the failure of the weir, and this is called piping. This process of erosion below the floor works backward and towards the upstream, results in the formation of a channel or a small pipe under the floor of the weir. Ultimately, this will cause the failure of the structure. This type of failure is called piping failure. So this failure can definitely be prevented by providing sufficient length of the impervious floor so that the path of percolation is increased and the exit gradient is reduced. So this hydraulic gradient would be reduced. If the hydraulic gradient is reduced, naturally the soil boiling condition can be avoided. Providing piles at the upstream and downstream ends of the floor to increase the flow path. So piles will be provided. So these are called the piles. Upstream pile, a downstream pile will be provided. Or another preventive measure is to extend the downstream portion and upstream portion of this foundation much beyond. So you need to design this total length. You need to design this total length both on the upstream side and downstream side, so that the flow of water which is entering into in the form of a pipe can be avoided, because you will be having a good value of the hydraulic gradient which shall not reach the critical or exit gradient. Another solution for this would be like to provide a pile like this. This is called the sheet pile. Upstream cutoff or sheet pile. Similarly, on the downstream side also a cutoff or a sheet pile may be provided. The second type of a failure for these weirs would be rupture of floor due to uplift. So the water which is percolating to the foundation exerts an upward pressure. This is what we have seen in the other structures also. Maybe a gravity dam. We have seen same type here also. The water which is available on the upstream side will have a tendency to flow, to seep through the foundation and move to the downstream portion. When this moving towards from downstream upstream to the downstream portion, it will exert an upward pressure, and this pressure is called the uplift pressure. If the weight of the floor is not sufficient to resist this uplift pressure, the floor may burst and the effective length of the impervious floor gets reduced, leads to increase in the exit gradient, failure of the weir takes place. Such failures occur in Chenab weir, also on Narora weir on the river Ganga. So rupture will be there for the floor due to uplift. You can see here in this figure also, you can see here, this is the downstream floor. So though weir is provided here, this is the downstream floor portion. Similarly on the upstream side also, there will be floor portion. So this upstream and downstream floor may be leading to the rupture, which is just because there is uplift pressure. There is uplift pressure. The failure of this floor by rupture due to these excessive uplift pressures can be prevented by providing the impervious floor of sufficient thickness at various points, and by providing the piles at the upstream and downstream ends of the floor to reduce uplift. See, for the failure 1, for the failure 2, the measures are same. The preventive measures are same. The first preventive measure is to see that you have to provide sufficient length of this concrete floor on the upstream side or also on the downstream side. This is the first preventive measure. Second preventive measure is to provide a cutoff or a sheet pile on the upstream side, also on the downstream side. Next, third failure will be rupture of floor due to suction caused by the standing wave. Standing wave is also called the hydraulic jump. As you just indicated, when the water is flowing from higher levels to the lower level, conversion of energy takes place. The water which is possessing more and more potential energy, when it is directly falling under the downstream portion, it gets converted into the kinetic energy. The result of which there will be change of state from supercritical to the subcritical state. So the standing wave, also called the hydraulic jump, will be developed on the downstream side of the weir, which causes the suction or negative pressure, which also acts in the direction of the uplift pressure. So with insufficient thickness of the floor to resist these forces, the weir fails by the rupture of the floor. Such failures occurred in so maybe on Chenab and Rezul river that occurred. The remedies for this type of failure will be to provide the additional thickness of the floor to counteract the extra pressure due to section of the hydraulic jump. So when you are designing the thickness of the floor at various sections, both on the downstream side and upstream side of the weir, we need to see that sufficient thickness is provided in order to take care of this section also. Then the second remedy will be to construct the floor as a monolithic concrete mass instead of having a masonry layer. Usually, if it is constructed in terms of the masonry layer, naturally the failure will be very frequent. Instead, if you construct a monolithic concrete structure, it will be like a mass concrete structure, monolithic without any joints, mass concrete structure, then it would be easy to prevent from this failure. Fourth one will be cover on the upstream and downstream of the weir. So with the concentration of the natural waterway of a river at the weir, the water may cover the bed of the river at both upstream side as well as on the downstream side ends of the structure. So the cover holes are so formed or may progress towards the structure. Ultimately, it will lead to the failure of the structure. It may lead to failure of the structure. So this is what is this covering on the upstream and downstream side. So the preventive measure for this type of failure would be to provide the upstream and downstream piles deeper than the cover. So if the cover depth is taken, you need to provide the upstream cutoff as well as the downstream cutoff, the sheet piles. The depth of those cutoffs must be more than the depth of the cover. Then to provide suitable length and thickness of the launching aprons on the upstream side and also on the downstream side, so that the stones of the upstream may settle in the cover holes. So this is how you have the four probable failures for the weir or barrage and the preventive measures also. So the one which we have seen is like piping, and then because of the boiling condition of the soil on the downstream side, piping may take place. Second one is that there may be a hydraulic jump which may be creating additional pressure. Third one is that there may be uplift pressure which may be causing instability to the foundation on the downstream side. And the fourth one is the scouring that may be taking place on the upstream side and downstream side of the weir. Also, we have seen for all these cases, the possible solution would be to provide the foundation both on the upstream side and downstream side, also to provide the foundation of sufficient thickness and to provide the cutoffs, sheet piles on the upstream side and downstream side. Also, the sheet pile, the depth of the sheet pile must be more than the depth of the cover to avoid the covering failure of the structure. Okay, so this is all one particular part. Second one is about the silt control devices. How to control the silt? As we already seen in the previous figure, in the first figure itself, the water is allowed to flow as clear as possible into the canals, as clear water as possible into the canals. So what we need to do? We need to see that almost or nearly fresh water should enter without having any sediment carried along with that. So two major devices are there which will be made as integral part, of the diversion network. They are the silt excluders and silt ejectors. They are provided in two different locations of this diversion network. Silt excluder, silt ejector. These two are the silt control devices. There are two types of silt control devices which are intended to prevent the entry of silt into the canal. Silt excluder and silt ejector, also called silt extractor. Let us try to understand this figure. You have the river, flow of water. So the direction indicates that there is a flow of water here in the river. You need the water to be diverted from the river into the canal. So if you want the water to be diverted into the canal from the river, just now we have seen we may construct a diversion headwork. So a diversion headwork is to be provided, and this diversion headwork may be consisting of a weir wall, a divide wall, a fish ladder, an under sluice, and then a marginal bund, and bunds will be provided on both the sides, and also should be provided with the silt excluders and silt ejectors. The entire thing constitute the total diversion network. So to the upstream of this off-take canal, you need to provide this structure, diversion network. Once this diversion network is provided here, the water level temporarily raises. Because of this rise of water level, the water enters into the canal. Our aim is to see that the water which is entering into this canal should be free from the silt or sediment material. When this water is flowing in this canal, along this canal, once again there may be another branch canal. This may be a main canal. So from the main canal, you may have a branch canal. So the water has to enter into the branch canal. So from river to the main canal, from the main canal to a branch canal. Further, by carrying for some more length from the branch canal, it has to enter into a major distributary. From the major distributary to a minor distributary to a field channel. This is what we have seen in our water resources engineering 1 also, while we were studying about the canal network. So while doing so, at different places, we try to see that the silt which is carried along with this river water should not enter into the canal. So within the river, at the upstream of this canal head regulator, we provide a device known as silt excluder. Silt excluder is provided within the river at the upstream of the canal head regulator. Thereby, the water enters into clear water enters into the canal. Then at the downstream of this canal head regulator, there will be another device known as silt ejector will be provided. Silt extractor or silt ejector will be provided at this portion. This is point 2 is the downstream of the head regulator. When the water is flowing here from the river to the canal, almost clear water. From the canal, once again, immediately after this head regulator, once again almost clear water will be coming out. So at this point, once again, it is getting diverted into another canal. So you may have a canal head regulator which is provided here. So this canal head regulator once again will have a device to see that the silt is controlled. So this is called a vein or a groin wall may be provided here to see that much clear water enters at this portion. Once again, at the downstream of this, that means once it enters into this offtake canal also, the same device like a silt ejector may be provided here. The purpose of providing all these silt ejectors or silt excluders is to see that nearly clear water is allowed to flow into the canal. Otherwise, what will happen? If the water with more and more silt flows into the canal, the entire canal may get silted up. This silt, the water with silt enters into the aggregate fields. The entire irrigated area also may get silted up. So to avoid this, we try to see that the water without silt enters into the canal, for which we will have two major devices known as the silt excluder and silt ejector. Of course, this will be in the after canal. Later we will see about that. Okay. So the silt excluder. So the silt excluder forms a part of the headwork from which the water is drawn into the canal. The silt excluder is a device provided in the bottom layers of the stream. A silt excluder consists of a number of rectangular tunnels, usually 4 to 6, covering 2 to 3 bays of the undersluices resting on the floor of the undersluice portion of the weir across the stream. The bottom of the tunnel is formed by the floor of the undersluice pocket upstream of the weir and in front of the head regulator. The top level of the roof of the tunnel corresponds to the level of the crest or silt of this canal head regulator. So this is the silt excluder. In the figure you may note here the silt excluder in the form of the tunnels. So these are all boxes. What we are seeing are the tunnels. So this will be provided at the undersluice portion. Already we have seen in the previous figure that there will be a clear weir wall, and for this weir wall we have a fish ladder and a divide wall. Followed by that you have the undersluice. So this undersluice may be within the body of the river, within the body of the weir, connecting to the bank. So at that portion, once again, there may be a canal which is directly connected with the diversion works, or like a head regulator, canal head regulator works. So you have this silt excluder which is provided in the form of these boxes. Let us see how this will work. So the tunnels will be there, and these tunnels, what are those tunnels? These are all the tunnels. So rectangular boxes. These tunnels are parallel to the head regulator and of varying length, the longest being nearer to the head regulator and equal to the length of the crest of the head regulator. These tunnels lead the flowing water below the crest level of the head regulator towards the covering sluice, also called the under sluice, to be discharged to the downstream side of the river, while the top layers of relatively clear water enter the canal trough through the head regulator. So that is how horizontally the entire flow of water is divided into two sheets. It is divided into two sheets. The sheet of water which is having more and more silt, as we know very well, the silt gets settled below the river cross section. So as the depth of water from the river is increasing, more and more clear water will be there towards the top. So if you see, there will be two layers of water. One layer of water with more silt concentration. The top layer will be with less silt concentration. It will be relatively a clear water. So what will be done? Because you are providing a tunnel there, so these tunnels will allow the water which is having more silt content, such water is to enter into the tunnel. More clear water will directly flow over the surface of the tunnel and flows directly into the canal. This is a simple mechanism that is provided. So water which is flowing through this tunnel, and you have two horizontal layers of the water. So the bottom layer of water having more and more silt content will be trapped, will be allowed only to flow through these tunnels, and the water which is more clear tries to flow over the top of the tunnel and flow directly into the canal. Yeah, this figure provides a very clear indication. You have several tunnels which are provided here, and the first tunnel is equal to the length which is equal to the total head regulator length. And as it is moving, the length of this tunnel also is getting reduced. These are all the tunnels which are provided like rectangular boxes. This total constitutes a silt excluder. Horizontally, the water may be having two sheets: sheet of water relatively clear with less silt content, and the bottom sheet of water having more silt content. When the water is flowing in this direction, because this is the weir wall. This is the weir wall and divide wall and fish ladder and the weir continuation. So these are the under sluice portion of the weir wall. So when the water is flowing here, the top layer, which is relatively clear, is allowed to flow over this top of the tunnel and enters into this head regulator. Okay, so the bottom layer, which is having more silt content, is not allowed to flow here, but it is allowed to flow only through these tunnels. So this is how the silt excluder. So what it will do? It will exclude the silt, the water which is having more and more silt content, suppress the clear water to flow through this head regulator. And finally, the water enters into the canal. Here. Okay, so this is how the tunnels, you may see here the size of the tunnel, how the length of the tunnel should be there, everything is given. The length of this tunnel also is varying. You may note that the maximum length of the tunnel will be equal to the length of the canal head regulator, near the river bank. Okay, so this is the seal or crest level, and you have the piers for the weir. So these are all the under sluice portion. So you have on the plan, you may note that. So these are all the tunnels. So the section is shown here. Near a rectangular openings are provided. So this is the silt excluder. Which is connecting with the canal head regulator. So you may see here opening for this sediment entry. The water which is having more and more silt content enters directly into the tunnel, whereas the water which is relatively free flows in this direction. Okay, then the capacity of these tunnels will be usually 50 to 20% of the canal discharge. Maximum velocity through the tunnel is 2 to 3 meters per second. If more velocity is there will be a problem that the silt also will be carried. So this is maintained to keep the tunnel free from the silt deposition, and height of the opening of the tunnel will be equal to the height of the crest of the head regulator above the floor minus the thickness of the head roof slab of the tunnel. Height of the tunnels will be usually 0.5 to 0.6 meters for the sandy river, 0.6 to 1.3 meters for the boulder stage rivers. Bellmouth entrance is provided at the mouth of the tunnel. The radius of the bell mouth in plan varies from one canal head regulator to the other type of canal regulator. The second one is the silt ejector. We have seen now we have seen now about the silt excluders, because the entire water layer is divided into two parts. Top layer relatively less silt flows directly. Bottom layer having more silt concentration and content is allowed to flow through the tunnels. So that is the silt excluder. Now the other one is silt extractor or silt ejector. You may see here, this will be provided, as we already indicated, this will be provided on the downstream portion of the diversion canal head regulators, and the water is allowed to flow in between these openings. You may see here, some of the openings are making a diversion of the flow of water. So you see a small wall is constructed, allowing the water to divert. So this is the silt extractor or silt ejector. So a silt extractor or a silt is a silt control device which is designed to remove the silt from a canal which has already entered into the canal. Of course, all the possible measures will be taken to see that almost clear water enters into the canal by providing the other silt control device known as the silt excluders. But what happened now here? Even after entering into the canal, if there is any silt content which is available, that part of the silt content may be removed with the help of these extractors, also called the ejectors. So this is provided at some distance downstream of the canal head regulator. Upstream of canal head regulator, we have other type of silt control device. At the downstream portion, the silt ejector will be provided, which is about 4 to 8 times the width of the canal. At the downstream portion, this will be provided. The silt ejector consists of a horizontal diaphragm slab a little above the canal bed. See that the diaphragm slab is provided a little above the canal bed. The diaphragm slab separates the bottom silt laden water and directs through a number of tunnels below the slab into an escape channel. So height of the tunnel is about 0.5 to 0.6 meters. The canal bed is depressed slightly by about 0.3 to 0.5 meters at the mouth under the diaphragm slab. You see here, this ejector is provided at the downstream portion of a canal head regulator, and so this is how the water enters in between these two, and a diaphragm slab will be provided here. Thereby, the tunnels are formed. Because there is a regular flow of water in this direction. The water is getting diverted into this, and it is moving into this escape channel. So the tunnels are so designed that there is no disturbance at the entrance, and the velocity of flow is quickly accelerated under the diaphragm to prevent the tunnels from being clogged. The discharge through the tunnel is regulated by the gates provided at the outlet end. The escape channel should have sufficient slope to carry the silt laden water without clogging the tunnels. The efficiency of these silt excluders may be taken to be E will be equal to QSA minus QSC by QSA into 100. QSA is the concentration of silt in the approach channel, and QSC is the concentration of silt in the channel downstream of providing any device, maybe a silt extractor or a silt excluder. Efficiency is the efficiency of the device. So silt, based on the silt concentration, we'll be able to arrive at the efficiency. The silt ejector is designed for an escape flow of about 20 to 30% of the canal discharge. Generally, the ejector spans the entire width of the canal. It is divided into 3 or 4 compartments, as we already seen in the figure. So these compartments will allow the water to flow, gets converged, and enter into the escape channel. The main tunnel compartments at the mouth of this ejector are subdivided into smaller tunnels by vanes of radii varying about 6 to 9 meters. The section of the subtunnel is constructed at the exit to increase the velocity in the main tunnel to about 2.5 to 3.5 meters per second. Height of the main tunnel may be about 1.8 meters to 2 meters to facilitate any of the inspections or any repair work or any maintenance work. The head required for operation is about 0.6 to 0.9 meters. So this is how the water gets diverted or escaped, allowed to flow into the escape channel. You can see here the vanes are provided allow the water to flow through these ways, gets collected and allowed to flow through the escape channel. At the canal head regulator, river training. We have seen about two basic devices like silt excluders and silt ejectors, and these two devices will be provided, one on the upstream side of the canal diversion work, canal head regulator, and the other one is provided on the downstream side. On the upstream side, when the water is entering from the river, to see that all the water which is more silted up is allowed to not to flow, it will be there at the downstream portion. In the upstream portion, well, relatively clear water enters into the canal. Even after entering into the canal also, if there is any leftover silt which is available in the canal, this also would be preferably removed by providing the canal some escape through the escape channel by providing the veins in the form of silt ejectors or extractors. Okay, so the last part, the last topic in the components of these diversion works is the river training work. River training work, that means we try to train the river, we try to allow the water in the river to flow through this regulator, for which probably you need to keep certain bunds on either side of the canal or extend these bunds. So at the canal head regulator, river training also shall be provided to maintain the smooth approach to the structure and prevent the river from outflanking the work. So this is accomplished by providing guide banks, marginal bunds upstream of the work to prevent the submergence due to raised high flood levels caused by the flux created by the weir. So the marginal bunds shall be continued till they join the high contours above the high flood level. You may see here, these are the river training works which are provided. The purpose of providing these marginal bunds or guide banks will be to allow to see that the water flows directly in the regulated river portion. Thereby the water can enter into the canal diversion works. So this is how the specifications are given for the guide banks, also the marginal bunds. Guide banks and marginal bunds. So that is the river training work. So what I'd like to show you here.